Hello everyone, welcome back to Coding Every Day. Today is day 13, January 28th. Today is a Tuesday at 4:04 p.m. So I'm looking at tree problems. So I did the linked list ones and then trees. I've did a couple of these. I got stuck on this one and now I'm just doing the next medium one. So I still feel a little inexperienced with trees. So I'm still kind of working through it. So let's see here. So given a binary search tree where all node values are unique and two nodes from the tree P and Q return the lowest common ancestor of the two nodes. The lowest common ancestor between two nodes P and Q is the lowest node in a tree T such that both P and Q are descendants. The ancestor is allowed to be a descendant itself. Okay, so here we get P equals 3 and Q equals 8. So 5 is the lowest common descendant. Here 3 and 4, 3. Okay. So I think I understand what it's asking. And then height of the tree. So we have two trees, or we have one tree. Yeah. Okay, so we have a binary search tree. And we have to find the lowest common descendant. And it must exist. It must exist. It will be the roots. The lowest common descendant. So I'm thinking you can just check if it's in the tree. So for instance, if like 4 is here and 3 is here, leaves, it's not possible for the leaf to be an answer because a leaf only has one node and we need two nodes P and Q. So if both of them are blank, so I guess I could say so if not root, then return. Also, if not root dot left and not root dot right. So this is leaf, then just return. So if it's null, then I don't think it should be null, but just in the edge cases of if we get a it could be. Okay, so otherwise we want to check if it's in the tree. So for instance, if we consider this tree, we check if 3, so if 3 is in the tree and 4 is in the tree, then we return root. Well, specifically, I guess we could say like if 3 is in tree and 4 is root, or if 4 is in tree and 3 is in roots, or 4 is in tree and 3 is. So if we want to check if a value is in a tree, so let's say like this will be the search function. So these mean it's not in there. If root dot value, so roots and then value. So if the value of the root equals value, then we return true. So if it's not a leaf and it doesn't equal the value, then we want to search root.left for value and search root.right for value. And if it's none of those, then we return false. So if I were to say print search P3, okay, so P equals 3, and that's like the head of or a root, right? Root is tree node. P I think we want to actually do this for root. So I just want to see if 3 is in the tree first. So I'm saying false. I think maybe I want it like that. And maybe I don't want that. So like I said, I'm not like an expert at trees or anything, so it's gonna take a minute here. Okay, so it's returning false, which is interesting. It's probably because I'm doing this. So I think maybe we do this. So if it's in either one, yeah. Okay, so now if I search for instance, 6, it should give me false because it's not in there. False. Okay, and it went through the whole thing. If I search, so Q is 8. So if we draw this tree, it'd be 5, 3, 8, 1, 4, 7, 9, 0, 2. 1 second. Okay. Search roots. So this would be null and then 2 here. That's an 8. Okay, so Q is 8. So if I search for, in Q, if I search for 6, that should also be false. If I search for something that's over here, like 3, that should be false, right? Okay, and if I search for 8, now it should be true. And same thing with 9, for instance. Okay, so I think this, wait, it says 9 is not in there. Five, 3, 8, 1, 4, 7, 9, 0, 2. Okay, so it prints all right, Alright, so let me print roots out left. So I guess I don't understand that. No, I get it. So why? Okay, so my question is, why does it say that when I search Q? Why are its children both none? Yeah, that doesn't make sense to me. What if I search P? So this is P equals 3. I wonder if it could have something to do with this. Okay, so the only place I print is right here. So I'm passing roots, and I'm looking for 9. Well, I also print here. So let me just call it. Okay, so 5, and now this one's saying that it has 2. And then it searches this one, which is 3, and then 3 has 2, and then it searches 1. It has none and 2. So then it will do 2, which has none and none. And then it goes 4, which is none and none, and then it does none and none. I don't think this should be necessary. So this should do the same thing. Well, these should return false. So root is a tree node. Or do I just return nothing? I don't think it works like that. That worked. Okay. So I just don't know why it says 8. Why it has nothing. So if we trace it, Q, and look for 9. So this gets skipped, this gets skipped. So now it returns search of left or search of right. Which this one should be, this will search left again actually. So this doesn't work. I could say if not r dot left and r dot right. Yeah, I honestly have no idea why it's... I mean, all of this doesn't, it's the same thing. I just don't know why when I pass in 8, it works. Or when I pass in root here, it works. So if I print that result, it will say true. But if I pass in, okay, what if I say root dot right? Does that also say true? Okay, so I think it's just the way that when I say Q. So what if I print the type of Q? It says it's tree node, but yeah, it says it's tree node. So weird. Because Q should be equal to, okay, let me see this. Prints if, So I want to print if root.right equals q. Okay. So it's different. But if I do root.right, then it's fine. So one of them gives me true and the other gives me false. But r.val should be equal to, well, no. This gets skipped because r is not null. This gets skipped because 8 doesn't equal 9. Could it be, well, this is integer? This is integer, no? Yeah. Well, actually, that's, so the one I'm passing is integer. And this one should also be integer. Yeah, this part makes no sense to me. I guess I don't understand what P and Q are. Because what I would do is basically just recurse and check for every node if P is in there and if Q is in there. Then we also have to do an H. And then we should also probably use the fact that it's a binary search tree. So for instance, if the target, so I shouldn't say val, say target. Hopefully that wasn't messing anything up. I doubt it. Yeah, okay, so if the target is greater than r.val, then we will search the right side. So root.right with target. Else, so r.val is less than target. r.left. So this uses the binary search tree, so we cut the problem in half every time. It's still, so that one still doesn't work for some reason. So I think it works. It just doesn't work for some reason when I use these parameters. So I don't really know how that's going to go. But but what if I make the target q.val, for instance? So if I say print roots, and then I say q.val, print search, like that, true. And if I say p.val, okay, so for every node, so I'll take Ancestor now, which takes in a root and p and q. So I'll make p and q values, and I'll say, so what I want to do now is so if we have this root, I want to check if q.val and, so if not roots, let's get out, if not roots, so if it's a leaf, I'll just keep it separated now for now. If it's a leaf, then I also want to get out. And then I want to search if search root p.val and search root q.val, then we found it. So we would return root. And the first time this gets called, it should be the right answer. And that might not be true. Okay, and if it's not, then what we want to do is we want to do an ancestor of roots. So p and q will just be values, I guess, that I so then I'll call it for both of this children. So roots out left, roots out right. Like this, all right. Well, won't this just give me the root though? Maybe I want it, I think I want it here. Like that. This returns a root, so dot val, I guess. 5. Is that the right answer? That is the right answer. It's probably a coincidence though. So same tree. but here P is 3. So okay, let me print here. So checking root dot val, and I want to see what it checks first. So first it checks 4 and then 3. So 3 returns false. Success. Okay, so it only works with 5. Okay, so I have to do something, so I'll be back. I think we're making progress here, though. I just have to figure out why 3 is being unsuccessful. And yeah, I'll be back. Alright, I'm back. I just sat down, so I think what I wanted to try to do was see why the second test case was failing. So unsuccessful search with, oh no, it says successful search with 3. And if I move this over here, will that do what I want? No. Okay, so it's... So maybe I could say found equals false. Non-local found. If found, return. And then here I could say found equals true. So that way it'll just stop. So checks 4, unsuccessful, checks 3, it's successful. Well, okay, so first it starts with 5, and then it starts with 3. And then 3 searches to 4. Okay. So 4 is a leaf. So it returns right here. So it just returns nothing. Then 3 goes. So 3. So let me get rid of this stuff. Let me just understand the order of what's happening here. Okay, so checking root, unsuccessful search with 4. Well, shouldn't this, oh, and I don't know if that will, yeah, so, okay, that makes more sense. So 4 should get filtered out. 1 is unsuccessful, 2 doesn't search, then it goes to 3. So checking root 3. So 3 is successful. So when it says successful search with 3, I just want it to like stop. So I could say maybe this here because that's where it was, right? So if I say if found return, so it won't do this for all the other calls. Your output was none. We don't want to return root. We want to whatever called this one. Could I just call found none? And then here I could say found equals root. And then if found, return found. Does this work? Okay. So the search is... Okay, I don't think I have the recommended time complexity here. So search is actually the right complexity because it reduces the problem size by half because we only search one of the subtrees. Now this is not O of H because for every node it does every other node. So this is actually 2 to the H, I believe. And we just want O of H, right? Yeah, because it searches every... So it's basically O of N. It searches every node. And it also has this jank. Okay. So the lowest common ancestor. Well, maybe we can use a number trick. So for instance, if P is 1 and Q is 2, we know that their parent... Okay, that's a bad example. So here we know that the parent's node must be 2 or 3 or 1. That's correct, yes? If this is 5, we could have 1, 2, 3, 4, 5. That's still the searching the height. But either way, so if we find P or Q, then we know what if we have 3, 1, 5? If we have 3, 2, 1, 5. So if you find a number that's in the middle of these two, or if you find one of the numbers, then you can get some inference. So if you find a number between p, so I'll say r dot val, so if it's between p and q, then okay, yeah, this is the way. So if you find a number that's between p and q or p and q, does p have to be less than q? No, p does not equal q. Okay, so first we'll find the minimum value. Let's just assume for now that p is always the minimum value. So if you find something in the middle of these two, so let's say like 3 and 8, if you find 6, okay, so if you find something in the middle, you know that q has to be somewhere in here, then p has to be somewhere in here. And I don't think there's anything more to it, because even if there's a 7 here, it doesn't matter, because if you found, but what if there's a 5? 5 could be here. But I think the first time you encounter something that's in the middle of the two numbers, then that is your least common ancestor. Because, okay, so let's look at this example. 5, 3, 8, 1, 4, 2, 7, 9. Okay, so P is 3, Q is 8. So we start from the root. We see that 5 is in between, is at least like the least value possible, the lowest node in the tree. So we find 5, and because 5 is between 3 and 8, we return it. Because there is no, we know that Q has to be on this side and P has to be on this side, just by nature, and it has to exist in the tree. Yes, they will both exist. Okay, so that's something for now. If P equals 3 and Q equals 4, 5 is not in between 3 and 4. Let's say we go to 8. 8 is not in between 3 and 4. 3, so we kind of want to do a breadth first. I don't know if you can do that. I'm sure you can. So So 3 is, so if the first one you encounter, is it just that simple? I mean, I could try it and see what sort of problems I get, but I'm just going to say if you encounter a number that is either P or Q, or is in between P and Q, then we return that number. Okay, so let's import. So I'm going to try to do like a breadth first search, because otherwise you could go down like a rabbit hole, right? Or does it not matter? Well, I'm thinking if it's H. Well, actually you could use a heuristic. So okay, so let's draw a number line here. Okay, so we have P and we have Q. Anything in orange, we found the answer. Anything in green, or let's just say purple. If we're in purple, that means we need to go to the left of the tree. And if we're in green, then we need to go to the right of the tree. Okay. Okay. So let's say min val and max val. Min value is the minimum between p dot val and q dot val, and max val is, I guess, I'll call them min targets, and max target is the maximum between these, and that's constant time either way. Okay. Actually, yeah, that's fine. Okay. So we want to first, if not root, then return. Otherwise, so if root.val is greater than or equal to, so I think we can say if root.val, so min val, max val, return root, like that. So if it's in the middle, we're good. Okay, if root.val is less than min val, so any of these, then we search lowest common ancestor. I'll just make another function because that's supposed to be tree node type, I believe, but I don't think it's statically typed anyway. So I guess I won't. So lowest common ancestor is, so we're going to pass root.right and then p dot, so p and q. Otherwise, no, not, that's, I mean, yeah, if we're at that point, it would be else, but okay, if root.val is greater than max val, then do the same thing, but now we want to use the left part of the tree. Okay, so this will return none, I'm thinking. Min target, max target. Yeah, so can we do that? Okay. Awesome. So I think that's actually in the heights in O of H, actually, because at every recursive call, we narrow the tree into half. And these both cannot be true, so it can't call both of them. So I think this is it. Let me see the solution. So recursion. So if the max val is less than, so that's what I have here, then you do the root dot left, yep. Otherwise return root if root or not p or not q. I don't have that part. Well, we know that p and q have to be non-null, right? They both exist. Yeah, awesome. Great. I'm happy I was able to walk that one through there. Feel pretty good about that. It was a little weird in the beginning that P and Q, it like wasn't like, which part? I was printing like print if for this one, if root dot right equals q and q equals 8, and it was giving me false, so I didn't really understand why. But yeah, this is great. I was able to logic that one through, and we got a solution. So thanks for watching, and we'll be back tomorrow.